Hi, we are now having another video, and this video is for Newton's laws of motion. Sir Isaac Newton was credited for being the first to describe the motion of massive objects, and he was able to formulate these three laws of motion. And these three laws of motion became the basis or became the fundamentals of an area in physics known as dynamics, where we study motion of objects in relation to the forces these which causes the state of motion of these objects. It describes how force influences the motion of objects, and there are, as mentioned, three laws. We sometimes call them as first law of motion, second law of motion, and third law of motion, but also they can be called as the law of inertia for the first law. You have the law of mass and acceleration for the second law, and law of action reaction for the third law. So let's start with the first law of motion, or also known as the law of inertia. So the law of inertia states that a body at rest will remain at rest, and a body in motion will remain at motion at a constant velocity unless and otherwise acted upon by an unequal and an unbalanced force. So basically what it tells us is the state of motion of an object will remain the same, either at rest or moving at a constant velocity, unless there is an external and unbalanced force acting on these objects. So let's say, for example, a book on a table will remain at rest unless and otherwise there's someone who will lift or who will push that book. A ball will continue rolling on the floor provided that there's no friction, unless and otherwise there is an unequal and unbalanced force acting on that ball. And that's where friction comes in because it opposes that motion, or it causes the motion, it causes the ball to change its state of motion, to decelerate. Now we have this property of an object that is referring to the tendency of an object to resist changes in motion, and that is inertia. And inertia is measured through the mass of an object. So what does that mean? The bigger the mass of an object, the greater the inertia it has. So when we look at objects with differences in mass, let's say for example you have a volleyball and a wrecking ball, which one is much easier to change its state of motion? If you are to move a wrecking ball and a volleyball, it will be much easier to change the state of motion of a volleyball compared to a wrecking ball because it has lesser mass. So another example to illustrate the first law of motion, or the law of inertia, we have here a biker that is moving towards the left, and the biker hits, or the bike hits a block here. As you can see, there's a block. So as this biker moves towards the left and the bike hits this block, the bike of course stops because it received a force that changed its state of motion. However, for the biker, it did not receive that force. That's why the biker will still continue moving to the left. So that's how we can illustrate the law of inertia. Let's give more examples so that we can understand more the law of inertia. So as stated, an object at rest will remain at rest just like this ball on the ground unless acted on by an unbalanced force. Unless and otherwise somebody kicks that ball will remain at rest. And an object in motion will continue to move with a constant speed and direction, just like this ball that is flying, that's moving through air, unless acted on by an unbalanced force. So when we look into balls that are moving, so eventually they stop because there is an unequal and unbalanced force. For example, your air resistance, the friction on the floor, and reaction forces from an object that it may hit. So again, the first law of motion tells us that an object will not change its state of motion unless you apply an unbalanced force, or there is an unbalanced force acting on that object. Another example, when we ride vehicles in jeepneys, in cars, or even in tricycles or in any other vehicles, when the drivers hit the brakes, of course the car decelerates, or especially if the hitting of brakes is abrupt, the car will put to stop. But however, since you are moving together with the car, as the car moves, you are also moving, then even though the car has now stopped, you are still actually moving forward. That's why you feel a jerk and you move forward when the brake is put to stop abruptly. That's why it's important to wear seatbelts. That is in accordance to the principle of inertia. Next, we have the second law of motion. And what's the second law of motion? That's the law of acceleration. So the law of acceleration tells us that the force acting on an object is equal to the mass of that object multiplied by its acceleration. Illustrated by, in our mathematical equation, we have force is equal to mass times acceleration. So once this force is actually net force. So once the force acting on an object is unbalanced, then you will have net force. And a net force will cause an object to accelerate. That's why when there's a net force, then there will be acceleration. Now, when we look into the relationship between our quantities here in the equation, force is equal to mass times acceleration. The greater the force, then the greater the acceleration. The greater the mass, the lesser will be the acceleration. Because in our equation, we have force will be directly proportional to acceleration, while mass will be inversely proportional to acceleration. We can express this as acceleration is equal to force over mass. So the greater the force, the greater the acceleration, the greater the mass, the lesser the acceleration. If we look at it conceptually, of course, when you have objects that are bigger in mass, for example, you have a cart, the other cart is full of groceries, and the other cart has empty or is empty. For you to accelerate the cart with groceries, then you will need more force compared to the empty cart. If you have the same cart, if you have two carts with the same amount of groceries, then if you double the force on the other cart, then you will have greater acceleration compared to the other cart. Now, since we are dealing with forces here, so the SI unit of force is Newton. It's important for you to remember that. A smaller unit is dyne. Smaller unit of force is dyne, and 1 Newton will be equal to 10 raised to 5 dynes. And also remember that 1 Newton is equal to 1 kilogram meter per second squared. So how did we arrive on that? As you can see here, your meter is expressed in kilograms and your acceleration is expressed in meters per second squared. So therefore, your force is kilogram meter per second squared. And that is also your Newton, which is the SI unit for force. So this is what we are talking about earlier. With the same force, if you have smaller mass, then you will have larger acceleration. With a greater mass, then you will have smaller acceleration, since mass is inversely proportional to acceleration. Next, we have here figure A and figure B. Figure A is empty while figure B is with 12 kilograms of load. So if we try to move or to accelerate these two carts, then you will need more force for figure B compared to figure A. So let's have an example to illustrate to practice solving the equation force is equal to mass times acceleration. So suppose that the net external force, which already included the push and the friction forces, exerted on a lawn mower is 51 newtons, or about 11 pounds, parallel to the ground. The mass of the mower is 24 kilograms. So what is the acceleration of the mower? So if our given values are, you have here force is equal to 51 newtons, and you have your mass is equal to 24 kilograms, you're asked about the acceleration. So to solve for acceleration, we know that force is equal to mass times acceleration. Deriving an equation for acceleration, that would be A is equal to F over M. So substituting your values, your force is 51 newtons over 24 kilograms. So your acceleration will be, if we input that in our calculator, you have 51 newtons divided by 24. That will give us about 1.125 meters per second squared. So this is our acceleration. Now, how did we arrive at meter per second squared? Remember that 1 Newton is equal to 1 kilogram meter per second squared. So if this is kilogram meter per second squared divided by kilogram, so kilogram gets cancelled, and you're left with meters per second squared. Another thing to remember when you do forces is that force is a vector quantity, meaning it's fully described with both magnitude and direction, as well as acceleration. So another example, a 63 kilogram sprinter starts a race with an acceleration of 4.20 meters per second squared. What's the net external force acting on that sprinter? So you have mass, which is 63 kilograms, and an acceleration of 4.2 meters per second squared. And you're asked about the net force. So what's the net force equal to? You have your net force is equal to your mass multiplied by the acceleration. Substituting your values again, you have 63 kilograms multiplied by 4.2 meters per second squared. So that's 63 multiplied by 4.2. Then you get 264.6 newtons of net force. So that is our net force for the sprinter, which causes the sprinter to accelerate at 4.20 meters per second. Now, another example, a 3 kilogram block is acted upon by a force where force is 3I plus 4J newtons. So as mentioned earlier, your force is a vector quantity. Therefore, it can be resolved into several components, or into different components. You have your x component, your y component, and your z component. Similar to acceleration, because acceleration is also the vector. So we have here two questions. Solve for the magnitude of the horizontal and vertical components of the acceleration of the block. So we need to solve for letter A, we need to solve for AX and acceleration in Y. For letter B, we need to solve for the acceleration of the block with the magnitude and direction. So how do we solve for your acceleration in X? What are our given values? So you have here, of course, the mass, which is 3 kilograms, and you have here your value of forces, your value for the forces. What does this expression mean? So this means that along the x, I is x, along the x there is 3 newtons, and along the y-axis there is 4 newtons. So to solve for ax, or the acceleration along the x-axis, we know that a is equal to F over m, right? So ax will be equal to the force along the x divided by the mass. Now, why is mass, or why does mass don't have a subscript x? Remember that mass is a scalar quantity, so it doesn't need direction to be fully defined. And of course, it will not make sense if you say 20 kilograms to the right. So it doesn't make sense. So this will be our formula to solve for the acceleration in the x-axis. So your force along the x-axis, again, as you can see there, it's 3I. So therefore, it's 3 newtons over your mass is 3 kilograms. So that will give you 1 meter per second squared. For your acceleration along the y, so that will be force along y over mass. So your force along y is, as you can see there, 4 newtons over, with the same object, 3 kilograms. So 4 divided by 3, that will be 1.33 meters per second squared. So these will be your components of the acceleration. Now we're asked to solve for the acceleration of the block. And how can we solve that? Since we have our components, then we can add these components to solve for our resultant acceleration. Your acceleration will be equal to the square root of the sum of squares of your ax and ay. So substituting your values, you have 1 meter per second squared plus 1.33 meters per second squared. Your acceleration will be equal to, if you put that in your calculator, that will be 1.66 meter per second squared. But we're not yet done. We need to solve for the direction of your acceleration. And if you remember your lesson in kinematics, your direction can be solved with theta is equal to the arctangent of your y divided by x. And your y here, your y component of the acceleration is 1.33. Forgot to write the arctangent. Let me write this one so that we'll have enough space. So you have theta is equal to arctan. You have y over x, which is arctan. You have 1.33 meter per second squared over 1 meter per second squared. So that will give you an approximate of 53.06 degrees. So therefore, your final answer here, your acceleration should be equal to 1.66 meter per second squared, 53.06 degrees north of east. So why did we say it's north of east? Remember, both of your components are in the positive axis. Therefore, they are in the first quadrant. So if they are in the first quadrant, then your direction will be north of east. If you plot that in a Cartesian coordinate plane, let's put that here. You have your x, which is 1, and then your y, which is 1.33. Let's say it's the position is there. So this will be your resultant acceleration or your acceleration, and this will be your angle. So this is east, this is north. So that's why it's north of east. So that's for the second law of motion, which is all about mass and acceleration. Next, you have the third law of motion, which is the law of action-reaction. And it states that in every action, there will be an equal and opposite reaction. So forces always come in pairs. And those pairs are known as action-reaction pairs. So when body A exerts a force on body B, then body B will also exert an equal but opposite force on body A. So we have here an example. If you push a wall, for example, with 100 newtons, of course, the wall will experience that 100 Newton force. That is the action. Now, what will be the reaction force? The reaction force will be the wall will also push 100 newtons or will also exert a force 100 newtons towards you, the one pushing the wall, towards the opposite direction. So those are your action-reaction pairs. Another good example to illustrate that one is when you punch a wall. So when you punch a wall, you exert force on the wall. That's the action. The reaction will be the wall exerts a force on your hand. That's why you feel pain, because the wall also exerted a force on your hand. Another example to illustrate action-reaction pairs. When you get off a boat, the reaction will be you are exerting a push force to the boat, directing it to the left in this example. That is the action. The reaction will be the boat will push you forward. That's why when you get off a boat, the boat seems to move backward and you will move forward. So that is the action reaction pairs. Action reaction pair. Another example is when you swim. So when you swim, your hand exerts a force against the water. That will be the reaction force. So you are actually pushing the water backward when you try to swim. And the reaction force will be the water will also exert a force to you, moving you forward. So that is the action reaction pair. And as you can see, it's always opposite from each other and it has the same magnitude. So always remember that. It's the in the third law, you have the action reaction pairs. Every action, there will be an equal and opposite reaction. Also, it's important to note that action reaction pairs do not cancel each other. Even though they are opposite and the same, even though they are opposite and they have the same magnitude, they do not cancel out each other. Why? Let's take a look at this example. Let's take a look at this example. You have here a swimmer. So the swimmer exerts the force to the water. So meaning the force is exerted on the water, that's the action. The reaction force is exerted on the swimmer. So they are not acting on the same object. That's why they do not cancel out each other. Action-reaction pairs do not cancel out each other. Unlike forces that acts on the same object, let's say, for example, you have here 3 newtons and another 3 newtons on opposite directions. Since they are acting on the same object, then they will get cancelled out. But for action-reaction pairs, they do not act on the same object. So let's have a sample problem. At a roller skating rink, a girl pushes a boy, causing the boy to accelerate at 1.5 meter per second squared to the left. The mass of the boy and the girl are 60 kilograms and 50 kilograms respectively. So we need to solve for the force exerted by the girl on the boy, the force exerted by the boy on the girl, and the acceleration of the girl. So when we look into the problem closely, you have here the boy and the girl in an ice skating rink. So supposing that the surface is frictionless, then you have here the girl pushes the boy, which causes the boy here, as you can see, to accelerate 1.5 meter per second squared. And the boy weighs 60 kilograms. The girl weighs 50 kilograms. So the girl exerted the force on the boy. So what will be the force of the girl on the boy? That is your first question. So for letter A, solve for the force of the girl exerted on the boy. So how do we solve for that? The object in question here will be the boy, since the force of the girl is exerted on the boy. Therefore, to solve for the force of the girl on the boy, we will use the mass of the boy and the acceleration of the boy. So the mass of the boy is 60 kilograms multiplied by 1.5 meter per second square. So the force of the girl on boy will be 60 times 1.5. So that is 90 newtons. Of course, that is a vector. 90 newtons left. Since your acceleration is towards the left, then therefore your force must also be towards the left. Now for question B, solve for the force exerted by the boy on the girl. So the force of the boy on the girl. Did the boy exert force on the girl? The answer will be Yes, because according to the third law, in every action, there will be an equal and opposite reaction. So the action was the girl pushed the boy, and the reaction will be there will the reaction will be the boy will also exert a force on the girl. And again, according to the third law, there will be an equal and opposite reaction. So if it's equal in magnitude, then therefore your force of the girl on the boy will be equal to the force of the boy on the girl. It's just that it will be opposite. Therefore, the force of the boy on the girl will be equal to 90 newtons as well. It's just that it's towards the rightward direction. Now, for letter C, find the acceleration of the girl or solve for the acceleration of the girl. So to solve for the acceleration of the girl, the force exerted on the girl is from the boy. Therefore, we'll use the force of the boy on the girl over the mass of the girl. And what's the force of the boy on the girl? It's also 90 newtons over your mass is 50 kilograms, the mass of the girl. So this gives us an acceleration of 1.8 meters per second squared. Direction is towards the right because the force is towards the right as well. So these are our answers for the problem. Yeah, here. So that will be our lesson for Newton's laws of motion. Thank you very much and bye.